All right, so now,
Even when it's cold, it's hot. Because when the sun is shining,
it's warm.
yeah, it's really warm.
Yeah.
Even if it's windy, cold, wind. Jeez.
Okay,
But it's tempered a lot, I mean, somewhat close to the sea, sorry.
it's all being recorded.
My words will be used against me.
All right, shall we start?
Yeah.
Yeah, all right, so it's a pleasure to have Promit here. So he's also going to tell us a friendly introduction to directed graphs in higher dimensions and their monoids. Promit, thank you.
Thank you. Thank you for this invitation. As you can see from the title, I'll mainly give an overview of this topic without going into technical details. So here is my plan for today. I will start with a basic idea about small categories. Parameters. And give you some basic examples. For those people who do not have any background categories or have a very basic like me, then I will talk about a particular example of a small category, which is somehow related with graphs called the path category. Then it will give me the perfect platform to define higher rank graphs. Next, I will talk about some geometric properties of this higher rank graphs. The second part, so this you can think as the part one. And the second part, I will talk about monoids, which one can associate with higher rank graphs. Talented monoid. Connection between the geometries of a graph and monoid. And lastly, if I get time, then I will want to talk about some moves on higher rank graphs and how they affect the talented monoid. Okay, so this is my plan. So let's start with small categories. So the category theorists know this very much. As a one-liner, you can say it's a category where the collection of all morphisms actually forms set. But there is also an algebraic definition you can provide like this one. So you have a non-empty set lambda, a distinguished subset, which we denote by lambda naught, lambda, and you have two maps, R and S, from this lambda to the distinguished subset lambda naught, which are going to be called the range and source maps, which satisfy these properties, which I am going to write. The first one is that if you restrict your range and source on this distinguished subset, then you will get the identity map. So that means your lambda naught is a retract of this lambda under both this range and source maps. Second one is that if you take any alpha from your lambda, oh, sorry, I forgot to mention that there exists another thing, a partially defined operation, which I denote by M from this pivot product to lambda. And then the second one makes sense. R alpha is same as alpha is same. So Third one tells that if you have two alpha beta which are composable, that means they lie in this pivot product, then their range is same as the range of the left one, and the source is the source of the right. Lastly, you have this associative. Roll alpha beta gamma in lambda alpha beta beta gamma. So this is, you can think of it as purely axiomatic definition of a small category. And then if you have two such small categories, say lambda 1 naught, R1, S1, another one lambda 2 naught, so R2 S2, then a map which preserves the structure will be termed as a functor. That means it preserves the range, preserves the source, and also the composition, right? So this is called functor. Now let's see some very basic examples. Since monoids are ubiquitous in mathematics, so why not start with monoid? So examples. Monoid. So if you have a monoid, which I used to write as a triple, this is the operation, this is the identity, then you can view this as a small category, right? Where lambda is actually this one, m, lambda naught is this thing, and R arrays are obviously defined because you have only one option, and the composition is the monoid operation. No. So this is a very simple example of monoid. Second one is you can start with any partially ordered set, or even you can start with a set with a pre-order. Let's take a coset B with a partial relation. Then you can view this as a small category. Lambda is this xy, xy and b. So the x less than equal to y. And your lambda naught is just this diagonal core xx. And obviously you can identify this with p. Range and source obviously defined. So range xy is xx and source xy is y. And the composition is using the transitivity relation. So you have another example of a small category. And the third one is interesting in our context, which is from a directed graph. So if you have a directed graph, E, then you can collect all the finite paths, which we usually denote by E star. Then this has a structure of a small category. That means lambda is here E star. Lambda naught is a set of vertices, which we view as paths of length 0. Range and source are somehow just the opposite of range and source in the graph. So it is the source of E, and the source is the range of E. And composition is the usual concatenation of paths. So I have these three very basic examples, but from here I want to highlight one thing is that, so let's talk about functors in this examples when we view this as small categories. So if you have monoids, then you can easily check that here functors are actually monoid homomorphisms, right? Because functors means they preserve the composition, and composition is the monoid operator. So they should be precisely the monoid homomorphisms. Similarly, if you have posets, here functors are nothing but order homomorphisms. That means maps which preserves the order. X less than equals to y imply fx less than. Now from this too, I think many of us may be tempted to say that if you have directed graphs, then functors will be graph homomorphisms. But this is not completely true. Obviously, any graph homomorphism is a functor, but every functor is not a graph homomorphism. Functors means it maps the vertices to vertices and morphisms to morphisms. But here morphisms, you are actually using this path category, right? So morphisms are paths. So paths goes to paths. That does not imply that edges goes to edges. So a functor may not be a graph homomorphism. So my question is that where these graph homomorphisms lie in the world of this path categories? So obviously they are functors, but which special type of functors are they, right? So to have this answer, we will change our view towards graphs. We will have a different view. So if you have a graph, we usually view this graph as a portable E0, E1, R, and S. But you can view it as a different way, in a different way. For example, you have this graph, right? This is the one vertex, one loop graph, formerly called the rows with one petal. And you can check that this is the terminal object in the category of directed graphs. So if you have any arbitrary graph, there exists exactly one graph homomorphism from E to this graph. Obviously, every vertex goes to this vertex and every edge goes to this loop E. So I can view this E as my graph E together with this unique graph homomorphism, which I have from E to this rows with one petal, right? Now, I'm changing my view in this way. I'm not just now viewing this graph only. I'm also viewing this unique homomorphism, which I have from this graph E to this rows graph one, R1. And then this is obviously a graph homomorphism, so it induces a functor between the categories E star and R1 star. A moment's thought will imply that this R1 star, this category of all finite paths of this rows graph, is isomorphic to this monoid viewed as a category n plus, right? And then this functor, which is induced by this unique graph homomorphism, is nothing but which assigns each path with its length p, right? So this is actually, in the language of category theory, this is the length functor L. So from now on, we will view a graph, a directed graph, as a pair E together with this length functor going to this path category of rows graph, or equivalently this monoid. And then I think this is a good position from where I can actually discuss the point of going in higher dimensions. So you look at here, this is a one-dimensional monoid, right? N. So the obvious way to generalize is that you replace this n by the k-dimensional counterpart, n. So now you have this k-dimensional commutative monoid, free monoid, n. And then you have, suppose you have a small category here, lambda, with a functor going to this monoid category nk t. Then why not we call this pair lambda e as a graph in higher dimensions, right? So graph in our one dimension, as we are viewing now, it is the graph itself with this functor L. And now going to higher dimension, the first thing you can do is that change this n to nk, and then this E star with an arbitrary small category together with this functor t from lambda to nk. So now I will call lambda d as a higher dimensional graph, but I need to put some condition on this functor t, which is also inspired from the property of this L length functor, right? So what is that? Now this length functor, the length functor L from E star to this n plus has a natural but interesting property. So suppose you have a path P in your E star, and then you put the length factor on it, and observe that the length of P is the sum of two things, m plus n. So for example, suppose you have a path of length 4, then you go here 4, and then 4 is, you can write it as 1 plus 3, 2 plus 2, 3 plus 1 in any way. But corresponding to each one of this factorization of the image, what you can do, you can split your path into two unique subpaths, right, of that length. So that implies there exist unique paths P1, P2 in E star, such that P is P1, P2, LP1 is M, and LP2 is N, right? And you can obviously do that in a unique way. So this is something we call the unique factorization property. And let me just tell you that it is a very restrictive property. You cannot always find this in arbitrary examples. For example, if you have this monoid n viewed as a category, then you can talk about a lot of functors between n and n. Because I have already mentioned that any functor is just like a monoid homomorphism. So you take this monoid homomorphism, x goes to 2x. This is obviously a functor, but this does not have this unique factorization property. For example, 3 goes to 6. 6 you can write as 1 plus 5, but there is no way to factorize this 3 so that the image will be 1 and 5. So this lacks this unique factorization property. Moreover, if you have this factorization of reversing factorization, that may not be in a unique way. So that's why this property is a very restrictive property. Now I am giving you the formal definition of the higher rank graph. Of pair lambda d is called algebra if lambda is a countably small category and d is a functor from lambda to this monoid category in K, which has this unique factorization. Satisfying UFP. Right. And then you can say that when you plug this K as 1, your higher rank graph, or mean one graphs will be precisely the path categories of directed graphs. So in this way, we have a generalization graphs in higher dimensions, right? And also you can now give the answer of my previous question, that how we can view graph homomorphisms in the world of these categories. So if you have two graphs now, say E and F, now I am viewing this as not only as E, but also together with this functors, right? So you have this length functor, and then a graph homomorphism, you can easily check that it makes this diagram commute, right? So graph homomorphism, the answer to the previous question is that a graph homomorphism F E to F is a functor E star F star, which has EWF. So these are the precisely graph homomorphisms of these functors, which has this unique factorization property. This is quite clear to see from this commutative diagram. So any functor which makes this diagram commute will obviously have this unique factorization property, and obviously you can check that any graph homomorphism has this. Okay. So from here, you can also talk about morphisms between higher rank graphs or higher dimensional graphs. What will be they? So if you have two higher rank graphs, lambda 1 and lambda 2, and now you know that higher rank graphs are come with these functors T, which we formally call the degree functor, replacing this length functor in higher dimensions. Then a functor F, which makes this diagram commute, will be termed as a morphism between these higher rank graphs. And then you can also talk about this category of all K graphs, where K is this K. This is the category of all K graphs, or higher rank K graphs actually, with morphisms defined as mentioned. Right. There is an alternative way to look at this category of K graphs. This is nothing but this comma category. So just take the category of all small categories, where the objects are small categories and morphisms are functors satisfying this UFP. And in particular, take this particular object NK. Then if you take this over category in this category of all small categories, objects lying over this NK, then this is precisely the category of K graphs. So there is another realization of the category of K graphs as a comma construction, right? Okay, so I think this is enough for the introduction. Okay, now let's talk about some geometric properties of higher networks. Before that, it will be good to give you the idea of some notations. So suppose you have a higher graph. lambda d. Then if you take any object or vertex and any n from this nk, then this p lambda n is the collection of all lambda such that range of this lambda is p and d of lambda is n. Right. Similarly, you can talk about this notation and also this notation with obvious meanings, right? But I only need this. So lambda is called row finite if this set phi lambda n is finite for all p and all n. So all our discussions will be for row finite K graphs. The first geometry I want to talk about is called aperiodicity. This is something which is related to the condition L, maybe you know in the level of directed graphs. So for this, you need the notion of infinite paths in a K graph. So there is the difficulty you have in the world of higher dimensional graphs, which we may not have in the case of one graphs. So for one graphs, it is easy to define paths and also infinite paths as the infinite sequence of concatenable edges, right? But that perspective is not possible here directly in this setup of higher dimensional graphs. So that's why we can think these paths in graphs in a different way. For example, if you have a path in a graph, E star, then you can view this path as a function from this poset category. How should I write? So let me write in this way, omega 1. So suppose P is a path with length n, right? So it's a finite path. And now I have this omega 1n, which is nothing but the poset category. I have already mentioned in the introduction that any poset gives you a category. So if you take the poset category of this principal down set, so everything lies below n. So n is a natural number, right? And then the morphisms are like this pair. So ij where I is less than j. Objects are like I. Okay. So this is a category, small category. And then you can view this path as a functor from omega 1n to this path category E star. How you are going to do that? So you just need to fix the images of these morphisms. So ij will go to, so suppose P is E1, E2, En, then mu of ij will be E I plus 1, I plus 2, j minus 1 j. So the portion of this path starting from the I plus 1 edge ending at this j edge. Right? In particular, mu p 0 n will be your path. Right. So this is a way to view any finite path as a functor, and you can extend this approach to view infinite paths. Just replace this omega 1n with omega 1. Now omega 1 is just the poset category of n. So you take everything natural. So that is also a poset. So if you take this as your domain, then any functor from this to the path category is nothing but an infinite path, right? And since this is a purely category theoretic approach, you can take this in your higher dimension, right? And then you can define an infinite path. An infinite path X in an HR graph, lambda is a functor from this omega k. So omega k to lambda. Right. So what is omega k is just the higher dimensional analog of this omega 1, right? Just the poset category of nk instead of n. And I have pictures to show you that how they look in the directed graph level. So yeah. So that's the picture. Yeah, I have already drawn. So here k is 2. And this is not the infinite one. This is the finite one, called the finite grid graph. And take this particular two tuple in. Then your category consists of morphisms of this sort, right? PQ have PQ in N2 such that P less than equal to Q in the coordinate wise ordering. And then you have only finitely many such nodes starting from this 3 to 6. And then you have this picture of this higher rank graph. Oh. So this is a way to define infinite paths in an arbitrary higher rank graph. And now we can talk about aperiodicity. So you have this space of infinite paths, which we denote by lambda infinity. So this is the collection of all such functors. X is a not only functor, is these are K graph morphisms. So X is a morphism. Right. And then you, for any P in NK, you can talk about the shift maps in this world of infinite paths, sigma P. There's like endomorphism, something like that. So take an infinite path X, goes here sigma Px. So that is also an infinite path. I'm claiming that, but I need to define its image. So sigma Px, if you consider its image of this, say Mn, and it is X m plus P plus P.
So deleting infinite number of entries here?
No, so here this is your morphism in here, right?
Yeah.
So m less than equal to n, and you have already this functor, so from omega k to lambda, right? So you have this thing xm. Now I am viewing everything starting from the position p shifted on the right. Yeah, what you tell is actually right in the one dimension. I'm just forgetting the first m position. But here things are complicated. You need to forget lots of things.
Do you forget an infinite number of things?
Hmm?
Do you forget an infinite
No,
number?
not infinite.
So-
It's still finite, but it's like not a single finite path. It's like an array,
Right,
initial block.
yeah.
Right. So this is the shape map. And then you can define aperiodic paths. So an infinite path X is called aperiodic if sigma px equal to sigma qx imply p is q. Not non-trivial shift can give you the same thing, right? So this is the definition of aperiodic, and your higher rank graph will be called aperiodic. Lambda is called aperiodic if for any vertex lambda naught there exists an aperiodic path x in lambda infinity such that x0, to be precise, it is actually x0c, right? x00 is the bottom element of your poset. So x00 is this. So this is the definition of aperiodic K graphs.
So in the one dimension,
Hmm.
is it the same as the adjacency matrix? Having some
No. Is there any criteria using adjacency matrices?
it's some power of it having non-zero entries.
That is something called irreducible.
It's different.
Yeah.
Okay.
The second property I want to talk about is there is also a notion of strong aperiodicity, but I am not going into that for time constraints. So let's talk about cofinality. This is very easy to define, but maybe hard to understand. So suppose you have some infinite paths. I'm drawing in this way, although I don't want to draw. Actually, you cannot draw in this way an infinite path in higher rank graphs. But for simplicity, let's draw in this way. So if you have an infinite path x and any vertex phi, cofinality means that there should exist some n in nk, such that if you look at this nth vertex n, which is actually mean this thing, don't be confused. So this is nn. So this is the image of this particular model. So there will exist a path starting at this vertex xn ending at. That's the definition of cofinality, or any x and any phi there exists some n such that v lambda xn, if you remember this notation, this is the set of all paths starting at this ending at here. This is not it. And this has something to do with the hereditary saturated subsets. I think you know hereditary saturated subset in the level of directed graphs, but there is also an analogous notion here. And there is an observation, or you can draw result, that lambda is cofinal if and only if set of hereditary saturated subsets only contains the trivial ones. That is something in your groupoid terminology, the minimality, right? So the graph groupoid or the boundary part groupoid of a graph is minimal if and only if these conditions have. Okay, so these are specific to geometric properties of a higher rank graph. There are many others, but I'm not going to that. Now, let's talk about the monoid, because I don't think I have many here. So, talented monoid. Oh, higher rank. So why I'm interested in this is that this is defined by rules in the directed graph setting, and then we have generalized this in the level of higher rank graphs, because this is something you can relate as the graded version of the ordinary graph monoids, which you have in the level of Leavitt path algebras, which are the positive cones of the graded the K theory, right? And these talented monoids are the positive cone of the graded K theory. So the definition is like this. Suppose you have a higher rank graph, HR graph. We have taken this graph to be row-finite and without sources. That means that this E lambda n, this is 0, infinity for all v and for all n. So if you have a higher rank graph of this sort, then first consider the free monoid generated by this thing. How should I write it? You can write it this way. So this is the free monoid generated by symbols of this short Pn, where P is a vertex and N is a k-tuple of integers, and then take the quotient of this free monoid with these relations. The relations are just defined on this generator. So if you have the generator Pn, then you can flow this in just using or resembling the Kunz-Krieger relations. Pn is something like the sum of this alpha. So you have here P, and you consider all those paths which end here, right, and have a specific degree, say d lambda m. This need not be the same n, this may be any m. So then you add this n plus m. Okay. This is the relation for all p lambda naught and n in set A. Also m in n q. So this is the definition of talented monoid, which I define in this way. Now there is a corresponding notion of graph monoids in higher rank graphs also, which just forgets these shifts written in the parentheses. But that's where the talent of this monoid comes. It actually captures this length, right? So if you have a vertex P, you have say W1, W2, W2. In the ordinary graph monoid, you will just write P same as Wi's, right? In the directed graph monoid, or even in this setup, we have also a notion of K-graph monoids. But in the talented monoid, you actually associate this length of paths. So somehow this lengths are captured in the definition. And that affects a lot when you try to characterize these algebraic properties of the algebra, which one associate with the higher rank graph has these monoids, right? Okay. And this monoid comes with the natural action of this free abelian group set K, d lambda, which is just going by increasing the shape. So if you have a shape Q, then acting on this generator results in n plus Q. This is a very easy definition of this action, but together with this action, d lambda becomes a zk monoid, and our program is to translate the geometric properties of the higher rank graph in the language of this zk monoid theoretic properties of the talented d lambda, right? So let me show you some instances with some examples. I think I have this. Okay, so this is an example of a talented monoid. So this is your 2 graph lambda, right? Green edges actually represent, the green represents edges of degree 1, 0, and red represents edges of degree 0, 1, right? And then this is the skeleton of this 2 graph. This is also related with the commonly known directed graph, which you call the cycle of length 4. This is actually the pullback of this cycle of length 4 with respect to a monoid homomorphism, but I'm not going to do that. Then if you write the relations of the talented monoid, you will have this sort of relations, and you can easily compute that the talented monoid is isomorphic. First, as a monoid with this direct sum of n, 4 copies, so n4, right? And this is not an ordinary isomorphism of commutative monoids. In fact, this preserves the action. So the action of this Z2 here and the action of this Z2 here, which I have not mentioned yet, how this acts on these tuples. So if you have a 2 tuple ij and it acts on a 4 tuple here, A, B, C, D, what is actually going on, it actually permutes these entries cyclically. So it is the permuted four tuple, or I should write in this way, four tuple permuted cyclically n times, where n is this thing. Right? So you need to add this I plus j and take the modulo with respect to 4, which is the length, and then just permute that number. And then it preserves the action. Okay, so there is an example. And then I have another example to show you that how the cofinality of a higher rank graph is related with the language of the talented monoid. So here you have a two graph lambda. Again, the green edges are 1, 0, and red is 0, 1. And these are the computation in the talented monoid. You can check that here the talented monoid is isomorphic to two copies of natural numbers. And the action is trivial. So ij, anything AB gives you the same, right? But this, if you just talk about this two graph and look at its geometry, you can observe that lambda is not cofinal, right? How I'm telling that? Because remember the definition of cofinality. If you have any infinite path x and any vertex, then there should exist some n such that v lambda xn should be non-empty, right? But here you can take this infinite path. Probably I should write as a functor from omega 2 to lambda, right? Because there is the definition of infinite paths in a two graph. So I am defining the images in this way. So I1, J1, comma J2. Again, remember the morphisms are pairs of this, right? So if you have I1, J1, I2, J2, you go here. So green are 1, 0, right? So Y1, I2 minus I1, and then Z1, J2 minus J1. So this is, in this way you can have, you have an infinite path in the K graph. This thing. But does there exist any n such that this W lambda xn is non-empty? In fact, you can check that for any n, xn, what will be the xn? Xn will be the vertex phi u, right? Everything is situated here. You're going nowhere, right? So the vertex, or I mean this thing, n comma n, this is p. U. Sorry, u. And then this is actually W lambda u, but there is no path starting from this u ending at W, right? So that means that this two graph is not cofinal. And if you now look at this monoid, you can have a non-trivial order ideal, right? So just take this, the n direct sum 0. Right. So since the action is trivial, any submonoid is actually an order. Any order ideal is actually a ZK order ideal. So this is a non-trivial Z2 order ideal of talented monoid, right? Z2 order ideal means it's the order ideal. That means a submonoid which is closed under the closed. How should I write? So if you have a submonoid in your monoid n, which has this property, suppose x in n and anything y which is less than x is also in n, then it is called an order ideal, right? And Z2 order ideal means it is an order ideal which is invariant with respect to the action, right? So here in the talented monoid, you have a non-trivial Z2 order ideal, and in the geometric setup, you have a K2 graph which is not cofinal. And somehow we have related these two things in this result. So this is a theorem. The following are equivalent. So, lambda is cofinal. The only heterosaturated subsets are the trivial ones. And the third one is the talented monoid property is that T lambda is simple as a ZK monoid. That means it divides of any kind of non-trivial ZK order ideals. So in this way, you can relate this talented monoid property with the geometric property, right? These can only even we have even more because we have a lattice isomorphism between the lattice of all these heterosaturated subsets of a higher rank graph and this lattice of all the ZK order ideals of talented. Right. So this is one instance how talented monoid captures the geometry of a higher rank graph. Also, there is an analogous characterization for aperiodicity, but that is a partial. Let me show you the example first. Yeah. So that is again a 2 graph.
It's like a magnetic field.
Right. Yeah. Here you have 3 vector arrows, you have 2 vector arrows. So again, these are 1, 0, and these are 0, 1. And this is the factorization rules. Okay, so you can check that. I think this is not very easy, but you can check that lambda is aperiodic. Right. Aperiodic, if you remember the definition, it means that there is an aperiodic infinite path which ends at each vertex, right? So here there is only one vertex P. You just need to exhibit one aperiodic infinite path. I think you can do that.
I believe it.
Yeah?
Yeah, I believe it.
Yeah, you can do that. So lambda is aperiodic as a HL graph. And now if you just take the talented monoid, you can find an interesting thing. This T lambda, remember there is an action of this Z2 on this T lambda, right? And this action is free. That means this is free action. I will say this is not very trivial to show, but we have the computation in the paper. So if you have something like this, so nx is x with n non-zero, then you'll have a contradiction. So that shows that the Z2 acts freely on this talented monoid. And then you have this result. If the group ZK acts on the talented monoid freely, then lambda is aperiodic as a HL. However, the converse is not true. We have some examples. The converse is true even if you put this restriction. If this monoid is atomic, which means that you can write any non-zero element as a finite sum of atoms. Atom means something like irreducible. You cannot decompose further, right? So you have this notion of atom. So in a monoid, an element is called atom if whenever U is written as P plus W, either P is 0 or W is 0, right? So if you can write any element of your talented monoid as a sum of atoms, then the converse also holds, right?
So is there like a one graph where this is the
Mhm.
converse is not true? Would there be a one?
No. Right. That's a good point. In the one graph level, these are if and only if.
Okay.
And there the aperiodicity is actually something which I have already mentioned, I think. There is the condition L.
Hmm.
Every cycle has an exit.
Hmm.
So that type of thing. Here you can also say that you have these cycles with exits, and that's why aperiodic. But here it is a strict thing to notice that this criteria of being aperiodic and cycles having exits or without exits, these are not if and only if in the higher rank levels, right? All right, so these are, I think I've counted 5 minutes. Okay. I'll just end with this pictures. Because of the time, I cannot give you the definition of these moves. So like the directed graph setting, here you have also some geometric moves, which leaves the sister algebra Morita equivalent, right? So corresponding to each HR graph, you can actually define an universal sister algebra, which is defined by Kumjian and Pask in 2000. And then after many years, I think in 2022, so 22 years after, they have actually tried to characterize the Morita equivalence between the sister algebras in terms of geometric moves of this higher rank graphs, right? But that is yet ongoing program. It is not finished. So they have defined some moves like this in splitting. Also, there is a notion of out splitting, sing deletion, and also there are some other moves called reduction. I don't know whether they have defined unital reduction or not, but they have reduction and also delay. So this is something like their inverse. Maybe this is the
This might be similar to
shift. Yeah, maybe. The interesting part is that, so if you have a HL graph, you in-split that graph at any vertex, you have a new HL graph, but the talented monoids are isomorphic. We have proved that. So if you have a HL graph lambda and consider its talented monoid, then it is isomorphic to the talented monoid of any of its in-split, right? And also the same thing happens here for the sing deletion move. So if you have a K graph lambda and you delete one of its sinks, remember here sinks, you may be astonished to see that this is not a sink. So I have written here this is deletion of the E2 sink P. That's why. So that is a E2 sink. That means it does not emit any edge in the E1 direction. It may emit edges in the E2 direction. Maybe here red indicates, red indicates E2. It emits edges of color green. That means it emits edges in the E1 direction, but not in the E2 direction.
But why is W coming? If you delete B,
And that's another good question, is that, which is again a difference between the directed graph and the HL graph, that if you delete this P, sometimes you need to delete all its out neighbors in this HL graph level, right? But in the one graph case, you don't need to delete all this. You just need to delete this, right? Because of this fact, because this P may emit edges in other directions.
Yeah.
Right. So that's why here I need to delete this W also. And you have this simple looking 2 graph lambda S, and you can easily show that this T lambda S, which is easy to compute, this is this dyadic natural numbers kind of thing. So how?
And what is the action?
Yeah, that's a good question again. So the action is something like this. So it does nothing with this M, it just increases here. Right. So the action of this E2 part is trivial. The action of E1 part is just increase 1 in this denominator. And these are obviously monoid isomorphism which preserves the action. Right. So in both cases, you have this. And that's actually something help us to tell that this moves of in splitting and sing deletion also leaves the graded monoid equivalence class of the corresponding algebra invariant. Because the big thing which we have proved for this talented monoid is that this talented monoid is isomorphic to the graded V monoid of this Leavitt algebra analog of algebras, which is known as the Combinatorics algebras. Right. Here you collect the equivalence classes of graded projective finitely united modules with respect to direct sum as monoid operation. And this is also a commutative monoid with nice properties. And this is isomorphism. So that means if these monoids are isomorphic, somehow this moves leaves invariant the graded monoid equivalence class of these algebras, right? Which I have proved directly also. But there is also a move which I have written here like reduction things. Here also there are several restrictions you need to put on your K-graph to reduce this. So here, for example, I have reduced this K-graph at P, 2 graph at P. That means you just remove all the edges coming out of P, and the edges which are going to V now will end again at dot, right? Because there is no P, right? Good. Oh, yeah. Do you have any question?
I had a question on the previous thing because
Okay.
I kind of from what I understand with the split move, you're splitting at V,
Mm.
and the partition is that you are putting the two green loops in separate elements of the partition.
Right, right. I think here one partition is
H1 and then H2. Or I guess H1 and
no, I have not given these names. I need to give these names.
oh sorry, but you have like one of the incoming red and one of the
You are
blues.
splitting the incoming ones, right?
Yes, but
So
what happened to the red arrow?
suppose this is F and G. So I think if I am not right, so in one partition you have this FH2 and in another one you have this GH1.
Yes. What I followed that, except what happened to the red arrow that starts from U and goes to W?
Oh, right, even one.
Okay, I didn't know if this was another
Yeah,
difference.
yeah, that will be there. Yeah.
Okay. Sorry, I'm gonna.
Thank you for finding. Yeah. Okay, so if you perform this reduction, then there is a result in their paper record at all that their sister algebras are Morita equivalent. But this is not a graded Morita equivalence, right? Because the lengths are changed. So here also in the level of talented monoids, you can check that this, this is lambda, this is lambda r, this T lambda is n plus n. But here T lambda r is one copy of n. But if you calculate the ordinary graph monoids, they are same. So that's why the importance of talented monoids are there. It captures the length, right? As I have previously mentioned. So something we have pulled that this may distinguish the class of Combinatorial algebras up to grade monoid equivalence, but we have already found counterexamples that it cannot do. But still we are trying to show that it at least captured the properties which remains invariant under graded monoid equivalence.
By the grading, so do you mean there's like some sort of
Yeah,
action on the sister algebras, some torus action?
yeah, the action of TK, yeah.
Okay. That preserves that.
Right. Right. So you can talk about higher dimensional gauge action.
Yeah.
Right, that's it. I want to finish.
Hey, I have hello, Promit.
Yeah, please share.
Promit.
Yes. Hello.
So you can mention the connection of talented monoid with groupoids. That means the type monoid of the skew product groupoid,
Oh,
like that.
oh, yeah. There is also connection of talented monoid with groupoids, or not a connection. You may say it's as a different kind of realization of a talented monoid is that. So suppose you have a K graph lambda. From here you can also build a groupoid which something resembles the infinite path groupoid which we have in the directed graph level. G lambda. I prefer this. G lambda. And then, so this is ample housed of groupoid, everything nice, not very difficult. So ample housed of groupoid, and then if you collect all the bisections, compact open bisection, you will have inverse semigroups, which is a sophisticated one called the Boolean inverse semi, right? And then if you collect its semi-lattice of idempotency and consider the type monoid, which is actually generated as the pre-monoid by this semi-lattice element under some relations, which actually resembles the Green's D relation in the literature of semigroups, I think. So then you have this type semigroup of this groupoid G lambda, and this is isomorphic not with the talented monoid, this is isomorphic with the ordinary graph M lambda. But instead of directly using this G lambda, if you take the skew product G lambda with the group set K with respect to this co-cycle, so you have this G lambda to set K. Here G lambda elements are same thing like this, infinite path groupoid. So X and Y goes K. With respect to this co-cycle, if you take the skew product and put this here, then you'll have this talented monoid instead of this graph. Something like we prefer to call it as the graded type semigroup, the groupoid. So that's a groupoid theoretic perspective of talented monoid, and something I think you can use to derive results about Steinberg algebra. Okay, thank you.
Thank you very much.
More questions?
Only Professor Shorter is there.
All right, thank you very much, everyone. Stop the recording.
Yeah,
Thank you. Why Sujit's name are different here?
yeah, it is his grandson name.
Oh, okay, right, right. So I thought Sujit came as incognito or something. Very good. I stopped the recording.
Yeah.